Hi, this is Millie Kay, and it's Friday, May 29th, 2020. The subject of this video is what's at the core of Oroville Dam. And I'll be showing photos and graphics from the Department of Water Resources galleries and reports, and reading excerpts from various publications that I'll reference in the information section below the video. And my goal, as always, is that we will all know a little bit more about the Oroville Dam than we knew before I made the video. And I'm showing, here in the beginning, I'm showing the initial phases of construction in a photo that was taken in 1963. They were damming up the Feather River. The Orville Dam is an earthen embankment dam in Butte County, California, USA, and it's the tallest dam in the United States. It's 770 feet tall, and it's built from clay, rock, and other natural materials. And the materials were obtained in and around the dredge tailing fields near the city of Oroville from the gold dredging. And more than 165 million tons of material was brought in for the building of the dam. So now let me show you the completed dam in this photo from 1968. It was at the time of the dedication ceremony. That's why you see all those cars and people there. So again, it was in 1968 that this photo was taken, and this shows the completed dam. And as I said, it's 770 feet tall, and then this is the axis of the dam. This road goes all the way across the dam, which is about 5,600 feet, so a little more than a mile. And I'm not going to do too much explanation of anything other than just the dam, except for one thing on this photo. This is the emergency spillway or auxiliary spillway weir right here. And as you can see, below it is just earth. It had not been armored upon the completion of the dam. Next, from the same basic angle, is a more recent picture, which is from June of 2019. And as you can see, the emergency spillway area has been stair-stepped with concrete. So again, looking at the dam from the same basic orientation, you can see the axis of the dam here. And then this is the reservoir side, and then the downstream side over here. And I wanted to show you those particular pictures so we can look at the dam and really get a little more comfortable with the graphics that I'm going to show. Here's the graphic on its side that shows what we've just been looking at. The axis of the dam here, reservoir side over here on the left, downstream side on the right. And we'll get deeper into this as we go. This is that same graphic, right side up. And then I did want to include, even though it's blurry, an engineering drawing of the dam. And it's, let me see. You can see that there are zones, and they're numbered. I know it's blurry, but the Oroville Dam can also be referred to as a zoned earthfill structure. And these zones are what we're really going to focus on in this video. And for that, I'm going to show you this really good DWR graphic from one of their publications. So now we're looking at the dam, just as we were in the first two photos, with the top, here's the axis of the dam would be up here. And then It was constructed in zones, and zone 1 is the impervious core. They call it the central clayey core. I just say clay instead of clayey, but the central clay core. And this clay core of zone 1 consists of a well-graded mixture of clays, silts, sands, gravels, and cobbles to 3-inch maximum size. And the compaction was in 10-inch lifts by 100-ton pneumatic rollers. And I don't know if I told you, but for the building of the dam, they brought in more than 165 million tons of material. So that's the central clay core. And really, it's impervious. It's an impervious clay core. And impervious means it's not allowing fluid to pass through. Although all, if not, well, I'd say most, if not all, earthen dams would have seepage. It's still considered an impervious clay core. And just to give you an idea of how impervious it is, according to the specs that I've read in several publications, the clay core is approximately 2 million times more impervious than the bulk of the dam. And another way of comparing it is that the average permeability of the clay core is 10 times more impervious than the material placed in 3-foot wide slurry walls in the levees downstream. So in those towns below their levee systems, they put 3-foot wide slurry cutoff walls to reinforce the levees. And this clay core is 10 times stronger or more impervious than those. And on each side of this clay core are transition zones. That's zone number 2. And a transition zone consists of a well-graded mixture of silts, sands, gravels, cobbles, and boulders to 15-inch maximum size. And the compaction was done in 15-inch lifts by smooth drum vibratory rollers. So that's zone 2. Then on each side of the zone 2s, there's zone 3s. And zone 3 is a shell zone of predominantly sands, gravels, cobbles, and boulders to 24-inch maximum size. And the compaction was in 24-inch lifts by smooth drum vibratory rollers. So zone 1, 3-inch maximum, zone 2, 15-inch maximum, and zone 3, 24-inch maximum. And zone 4 is also impervious core. It has a little different specifications than zone 1, but it's impervious core material. And 4A down here is a buffer zone. It's designed to compress with it has the same grading requirements as zone 4, but the compaction is not as dense. It was in 15-inch lifts by a smooth drum vibratory roller. So that's zone 4A, buffer zone designed to compress. And 1B is the same as 1. It's just not red in this photo, but it's the same makeup as zone 1. Now, let me see. So that pretty much covers all the zones except for 5. 5A and B, this is a drainage zone, and it consists of gravels, cobbles, and boulders. The I won't get into the specifications were like about the sieve size, but its compaction was in 24-inch lifts by a smooth drum vibratory roller. And I'll tell you about the drainage system, this 5A and 5B. The key barrier for seepage through the dam is the central clay core. And remember, it's 27 feet wide up at the top and about 300 feet wide down at the bottom as it sits on the core block. And so it's the key barrier for seepage through the dam. And the key barrier for seepage through the foundation is below the core. They bored holes in the bedrock beneath the core. This red line here shows the clay core is founded on the concrete core block in this really central section of the dam. And that's to prevent differential settlement of the core, which, as I understand it, it was really like uneven. They can't get that even of a surface in the area they're working in. So then they put the core block for the stability. And the core block is 283,000 cubic yards of concrete is what that's made up of. So when there is seepage and it goes through this central clay core, it is intercepted by this gravel drain system. And then the seepage flows, it goes down, and then it flows through a low internal pool is what this is called. And then it goes through a pipe. It goes into a weir house. It's a vault with that has a weir so that they can measure the output of the seepage. And then the water goes on down the river. I'll show you a picture of that weir house. It looks like this. So that's where they measure the water, the seepage that's coming out. So that's built right into the dam. Now let me go back and tell you a little bit about how much seepage. During dry seasons, the average seepage, according to the Department of Water Resources, is about 10 gallons per minute. That's what's measured at this weir at the vault house. So about 10 gallons per minute in dry season. And in wet season, the seepage flow would get up to about 100 gallons per minute. And they've measured this since the building of the dam. And just in comparison, according to Department of Water Resources, even large zoned embankment dams that are smaller in height from the Orville Dam they commonly would seep several hundred gallons per minute. So 100 gallons per minute is excellent. And just to summarize, this dam was built to it incorporates design elements that reduce the seepage. That's the central clay core, reduces the seepage, intercepts the seepage, this whole drain system that was built to intercept the seepage that does come through, and then to send the seepage to a place where it can be easily monitored. Now, let's go back to the core block. I told you it's 283,000 cubic yards of concrete. And it it cracked during the construction. And I will explain that by reading an excerpt from the American Society of Civil Engineers publication from 1977. And they explain it that the core block was damaged by excessive deformations induced by embankment loads during construction. Structural cracking, more than 500 feet in length and with width varying from 1/4 inch to 6 inches, impaired the hydraulic and structural performance of the core block. Over 6,000 bags of cement were injected in various grout mixes in several continuous grouting operations to fill the cracks. Hydraulic plugging of an impaired drainage gallery was accomplished by intrusion grouting of pre-placed gravel. Repairs were successfully carried out by the grouting program, and excellent hydraulic performance of the core block has been realized over the 8 years since the subsequent completion of embankment construction and reservoir filling. So that was in 1977, which of course, brings up the question of how's it holding up? And that is something for further research. It's not going to be part of this video, but I would like to see if there are any issues or if there have been other issues since 1977 and what they are. And I'd have to read inspection reports and really dig pretty deep for that. So that might be something for a future video. Now I'd like to show you, we looked at this. Okay, this is blurry because it's a screen capture of something that was already blurry, but this is the list of the instrumentation at the Oroville Dam that was put in when it was built. And this dam was state-of-the-art when it was being built, and it was called the Talking Dam because it had so many instruments embedded in it to give them information on seismic activity and water pressure and soil stresses. And so this is the whole listing of what they had put in. And what I want to focus on are at the top here, there were 54 hydraulic piezometers put in the dam embankment, and there were 2 hydraulic piezometers in the dam foundation rock. And this, I'll read from the recent April 17th, 2020, the California Department of Water Resources Lake Oroville Community Update. And it's about the installation of piezometers at Oroville Dam being completed. DWR contractors have completed installation of 8 new piezometers at the base of the dam. These moisture sensing devices will further DWR's efforts to monitor seepage and will be used to confirm the seepage measurements DWR already collects. Seepage is normal and expected, especially in large earthen dams like Orville. Seepage is measured and collected through a drainage system. If seepage were to change dramatically, it would indicate an issue that would need further investigation. This work is part of the early implementation of the Oroville Dam Safety Comprehensive Needs Assessment, CNA, which is focused on identifying priorities and appropriate solutions to bolster the integrity and resiliency of the Oroville Dam complex to ensure public safety. There were 56 piezometers initially installed in the dam 50 years ago, which, as anticipated, have since stopped functioning. DWR plans to install additional piezometers throughout the facility in the coming years. So this information really concludes this video. I want to leave you with this photo. It's a black and white photo from 1963 of the construction phase, early construction of the dam. And I want to let you know that if you hit the subscribe button, whether you're already subscribed or just subscribing, if you let it drop down and hit the all notifications, you'll be notified when I upload a new video, and also of periodic messages that I might send through the community tab. And I welcome and encourage productive discussion about the content of all my videos. And so many of you have followed my channel since 2017. I sincerely appreciate your interest and support, whether you're an early subscriber or a recent one. And I hope that you will like, subscribe, and share this video. And I'll see you later.